Okay, hello everyone. We can get the last few people in to find seats. We about set. Welcome to the SIU Climate Solutions Teach-In. We are part of a global movement, and you all got to experience some exciting weather today, and we're very glad that we made it through the thunderstorms. We are indeed part of a global movement. There are about 350 events going on, mostly today, but overall this week, and in almost every US state and in about 50 different countries. And I started planning this way last summer, and many of you have been involved, so thank you all for participating in this event. The main thing I want to let you know, actually, I'll take a pause here and let people in so they can sit down here. Come up front wherever you want to go. Come on, move in. Don't want to have you standing there for half an hour. Great, thank you. Thank you all for coming again, thanks. I have just a little example here about how this is an interdisciplinary issue. Climate change is an interdisciplinary issue. So in other words, it goes across disciplines or it goes across majors, right? So many students are from different majors who are here, and climate change impacts really all of us and even your field of study. And I hope most of you saw our posters around campus, this beautiful image from an artist, Alyssa Singer. But what you may not know when you just see the pretty image is that it's actually based on actual climate data. So this is data from NOAA, and it's the December temperature. So the average temperature, what you would expect in December, is sort of that line between the blue and the red. And then cooler than normal years are the blue. You can see that mostly 1880s through maybe 1940s, 1930s. And then the reds start popping up. And then you can see here, really since the 1980s, the red. So that would be higher than expected December temperatures. But then think about taking that and making it into artwork. That's pretty cool. That is such a great example of how climate change is an interdisciplinary concept. We all in all disciplines need to think about climate change. I next want to introduce our brief keynote speaker who will talk about the 5 essential facts about climate change. He is our campus climatologist, a wonderful colleague, Dr. Justin Schoof. He's the director of the School of Earth Systems and Sustainability and a professor in geography and environmental resources.
Thank you, Dr. Duram. It's great to see everyone. I mean that sincerely. I think this is the first event that I've been at since the COVID pandemic started, and it feels great. So it's just really nice to see all of you. The other thing that I want to do before I start is I want to have everybody join me in thanking Dr. Duram. Those of you that are involved in the event today know that she has put a lot of work and effort into making this the event that it is, and I expect that it's going to be a fantastic event. I want to clarify that I'm not going to be talking about the 5 most essential ideas about climate change, just 5 things that I thought would be useful for this group to know. So I'm not going to keep you in suspense. Here they are, and then I'll talk about them. So fact number 1 is that climate change is occurring throughout the interconnected climate system. Fact number 2 is that climate doesn't change the same everywhere. Important regional variations exist. Fact 3 is that many aspects of observed climate change can already be confidently attributed to human activity. Fact 4 is that the longer that we delay meaningful action, the harder it will be to achieve the same outcomes. And finally, individual actions matter, but this is a problem that's so large that we need broad action on climate change that goes beyond personal choice. So I'm going to talk about each of these things in turn. As Dr. Duram mentioned, I'm only going to go for about 15 minutes. So this isn't going to be really long. And also we don't have any time for Q&A, but I will be around tonight. So if you hear something interesting in my presentation and you want to talk about it more, just find me and I'll probably be happy to talk to you about it until you don't want to talk about it anymore. Okay, so this is probably the figure that many of us have seen or something like it that tells us that climate change is happening. This is the global temperature record. This is from NASA, from Goddard. And basically what we're looking at is departures from the 1951 to 1980 average for temperature. Now we can look at this figure and we can say lots of interesting things about climate. We can say that the 10 warmest years on record, well, 9 out of them are in the last 10 years. Okay, we can say that each of the last 4 decades has been successively warmer than the one before and warmer than any decade since 1850. Okay, we can say things like that with this data that I think would be enough to convince people that there's an issue. But of course, there are folks that look at this record and say, well, there's problems with the stations. Cities are becoming urban, so it's an urban signal, right? Well, we can look in a lot of other places, and that's the point that I want to make. How about ocean heat content? Here are several examples. The one on the left is from the full ocean depth, and the one on the right is just the top 2,000 meters. We know that the oceans are becoming warmer, and if we had better data, this is probably a better representation of global warming than the air temperature record is. How about global mean sea level? Okay, so again, on the left, since 1850, lots and lots of data sets. You can go study them on your own if you want to. And then on the right, the more recent period, clearly showing notable increases in sea level over the period of record. Ocean surface pH. So one of the things that those of you that work even maybe tangentially to climate are aware of is that as the ocean absorbs CO2 from the atmosphere, it becomes more acidic. So what we're actually seeing here is a tendency towards the oceans being more acidic over time. How about changes in the large ice sheets covering Greenland and Antarctica? We can see very clearly from this figure, just going back to the early 1990s, that both of those ice areas are losing mass quite rapidly. This is especially true in the northern polar region. How about mountain glaciers? Again, the figure on the left shows the number of advancing mountain glaciers with the current time being 0 and 2000 being 2000 years ago. We can also look at mountain glacier mass balance using studies that are shown there on the right side of the figure. Also a little bit noisy, but a clear downward trend over time. How about snow cover extent? So we don't really necessarily think about snow cover extent as being a sensitive climate variable, but it really matters because snow is brightly covered. So if you have the surface covered with bright snow, it behaves very differently than if it's covered with the underlying grass or soil surface. So we know that there's a decline in snow cover extent over time too. So if we want to kind of sum this up, we have lots of evidence for climate change. In the air, we have evidence of changes in atmospheric circulation, air temperature, water vapor content, et cetera. In the oceans, we see increases in sea surface temperatures, sea level, changes in species, acidification, ocean heat content. If we look at the ice, we see loss of permafrost, we see loss of ice sheets, we see loss of sea ice. And if we go to the land surface, we see increases in global greenness, species range shifts, all kinds of stuff. The point I'm making here for essential fact 1 is that climate change is everywhere in the system. We don't rely on one record to determine that climate change is happening. Okay, on to fact 2. Climate does not change the same everywhere. Important regional variations exist. So this is what NOAA calls the land ocean temperature index. So it's basically just the temperature anomaly. But what we're looking at here is the trend from 1880 to 2020. So this is over the period of record, and you can see that almost everywhere has warmed. The gray areas don't have sufficient data, but almost everywhere has warmed. There are a couple of exceptions. For example, the area where deep water forms in the North Atlantic, we don't have warming there. But generally, almost all of the world is warmed. But if you look on the right, you can see that the warming is not the same during the winter and the summer. So this is Northern Hemisphere winter on the top and Northern Hemisphere summer on the bottom. And you can see that the warming has been the greatest during winter at the high latitudes of the Northern Hemisphere. So when we talk about the future and we talk about climate change greater than 4 degrees Celsius, that's already happening in parts of the Arctic during winter. It's already happened. So we shouldn't be thinking about this as something that is, you know, going to happen. It's already happening. In some places, it's already happened to a large degree. We can also see this as sort of a pattern scaling, so that as the world becomes warmer, we know that some regions are going to warm more than others. So for example, at 1.5 degrees of warming, almost all the land areas warm more than 1.5 degrees, because land areas warm more than ocean areas. So we're talking about 4 degrees Celsius of warming on the right. We're not talking about 4 degrees Celsius over land areas. We're talking about much greater trends over land areas because the air over the oceans will warm less. For precipitation, it gets even messier. And the reason is that precipitation doesn't just depend on the amount of water vapor in the air. It depends on the transport of that water vapor to areas of convergence so that we can get things like thunderstorm development. Okay, climate fact number 3. Many aspects of observed climate change can already be confidently attributed to human activity. So the image on the left there is a very simple one. It shows how much global warming we've experienced. This is just in 2010 to 2019 relative to 1850 to 1900. So what we're saying is that that one decade was about 1 degree warmer than 1850 to 1900 was. So 1 degree. You say, well, where did that warming come from? How can we attribute that warming to some cause? Well, here's how it breaks down. How much of the global warming is attributed to humans? All of it. You can see that the line for total human influence matches almost perfectly the magnitude of the observed trend. That's because of some cancellations. So for example, the effects of greenhouse gases actually warm us more than we've warmed. But that's partially canceled out by the effects of other human drivers, which tend in this case mostly to be aerosols. So aerosols have a cooling effect that's partially masking some of the warming that we've been experiencing related to greenhouse gases. You can also see the solar variability, the internal variability are very small on this figure. In other words, they've contributed very little to the warming over that period. I won't talk in detail about the figure on the right, but you can see how those anthropogenic effects can actually be broken down even further into individual causes. Those have some error bars on them. This isn't perfect, but this is getting close to where we are in terms of attribution. Here's another way of looking at it. We can look at these same effects over time. So we know when the volcanic eruptions have happened, right? Those are those big negative excursions. We get cooling of the atmosphere after a volcanic eruption. But you can also see on here the effects of carbon dioxide, methane, solar activity, other anthropogenic, and so on. And then let's see here, the total, this is the forcing. So this is actually what might cause the temperature change. So this is like the energy going into the system. And then this is what the temperature changes look like as a result of that. So if you look at the observations there shown by the black line, you can see how that relates to the very strong warming effects from greenhouse gases, the cooling effects from aerosols, which are also a human effect, and then the combined human and natural, which put us basically in an envelope right around the observations. What this tells us is that we can't reproduce the known history of the Earth's climate without considering the natural and the human, but over this period of time, the human factors are the dominant ones. Okay, fact number 4 is that the longer we delay meaningful action, the harder it will be to achieve the same outcomes. We've heard a lot in the last couple of years about 1.5 degrees Celsius targets or 2 degrees Celsius targets. This is the 2 degrees Celsius target. And it shows us the lowest box here shows us the line that we would have if we had started mitigation in the year 2000. We would have required a mitigation rate of 2% per year in terms of lowering our carbon emissions. In order to do that now, if we started in 2020, now we have to do 6% per year. There's a huge difference between 2% reduction per year and 6% reduction per year. And basically, if we go much further down this path, this is where the whole 11 years to act kind of stuff comes from. Because if we get far enough down this path, we will not be able to keep warming below 1.5 to 2 degrees Celsius without having to rely on unproven technologies to remove carbon dioxide from the air. Another way of thinking about this is that, well, on a personal level, I didn't really like the 1.5 degrees C approach. And I think that the climate science community has sort of come back from that a little bit and said, listen, every amount of additional warming matters. 1.6 degrees of warming will result in more suffering than 1.5 degrees of warming. And so I like to think of this a slightly different way, which clarifies the climate change issue for a lot of people. The amount of warming that we get on Earth is directly related, as you can see here, almost linearly related to our total emissions of CO2 in gigatons. So you hear people talking all the time about future scenarios run by the IPCC. Which path are we on? The answer is it doesn't matter. They're all the same. The difference between these boxes is that they all end at 2100 with different levels of CO2 emissions that are shown on the x-axis. The only difference is that we emit more carbon under some of them than others, and we get more warming as a result. The amount of warming that we get in the climate system is almost linearly related to the amount of CO2 that we collectively emit. Okay, final climate fact. There's no pictures with this one because it's just my thoughts. Individual actions matter, but we need broad action on climate change that goes beyond personal choice. I want to start by saying that I'm not putting down personal choice. I think personal choice is very important in this problem. So, whether we decide to adhere to a particular diet, whether we decide that we're not going to travel internationally, whatever it might be, they matter. They matter for climate and they matter for other positive, life impacts. However, most of our global carbon emissions result from the stranglehold that is held on society right now. And that is our reliance on fossil fuel-based energy and transportation. So if we're going to solve climate, we need solutions that will address reducing and moving toward full elimination quickly of fossil fuel-based energy sources across society. And the part that I want to stress is that this must be true even for people who don't care about their carbon footprint. Okay. I'm going to go back to my title slide and just say that I've provided what I hope is a nice kind of overview of the physical science of climate and some of the major issues. But the thing that's going to make tonight's event so special is that we have experts among our faculty and students that can really talk to us about climate from the perspective of impacts and adaptation and how it affects all of us across disciplines. So I'm going to stop there. I'll turn it back over to Dr. Duram.
He set that up very nicely. So there are two terms that he just used. So I thought I'd start with just a few very brief definitions so we're all on the same page when we're talking about solutions this evening. But again, the concept of being interdisciplinary, you can think about how this fits into your major, your interests. But we need to think about mitigation, which is this idea of reducing climate change. These are definitions from the NASA website. So in other words, reducing the flow of greenhouse gas emissions. Dr. Schoof talked about that just a bit. So that's kind of a before thing. So these are solutions we can take, changes in society we can take now to decrease the impacts of our emissions, to decrease climate change. So that's mitigation, kind of before, although it's a little late to be before, we're already in the middle of it. So it's sort of before and during. And then adaptation are the things that we do to deal with climate change, to live our lives, given that we're in the middle of climate change. So in adjusting our actual or expected lives to deal with future climate. So that's sort of the after and or again, during. We're already during, so there's not really a before and after, but just kind of think about mitigation things are things, actions we can take now to reduce our impact. Adaptation is what we'll all have to do to survive with a changing climate. Another concept I want you to think about then is impacts. And I've divided these two up between maybe more natural world and more the social world, if you will. But many of the student presentations that you saw up front, and actually let me shout out to my environmental studies students who did all of the presentations. But you saw different examples where there was species are being impacted through threatened and endangered species, habitat loss, that sort of thing. Landscapes, we see this in the news all the time between forest fires, droughts, and also flooding in various parts of the world. Dr. Schoof mentioned issues with our oceans, rising temperatures, acidification, and so on. And then in terms of society, and I think a lot of the panels this evening will be addressing some of these social concerns, but there is a real inequity in who is being more harmed by climate change, right? It varies from place to place. It varies by income level. It varies across society, across the planet. So there are social issues we need to think about in terms of inequities. There are also just simply people issues where we see increasing numbers of climate refugees. And think about that impact. Like we already know where we are on those charts in terms of temperature and so on, but what does that look like in 10 or 20 or 30 years? And the numbers of people who may have to move because of climate change. And then likewise, there are different issues that are economic that impact all of us, whether it's increasing costs of food, increasing costs of housing, and so forth. And then finally, what we're here for, we are here to talk about solutions. There are individual actions that you can take. Buy an electric car, by all means. If you can afford that, do that. If you can put solar panels on your car, by all means, do that. Other smaller steps you can take: eat a more plant-based diet. It is lower in emissions. And simply buy less stuff. All the stuff you buy is based on fossil fuel. So that stuff, that thing you buy and then throw away, you're causing emissions. Every one of those things is a little check mark towards those higher emissions. In terms of policy, we can talk about local, national, and global policies. Some people here today will be talking about policies, but the big picture is vote for people who will take action on climate change. So that's sort of a mixy-uppy thing there, because it's an individual action that everyone in this room can take. And it is something you should be concerned about, because when we talk about these big societal issues and we talk about the policy actions that we need to take, you have to vote for the right people to get those actions in place, to get those things rolling. And then finally, and this feeds perfectly into our whole panel, all of our panel discussions, but basically there are a lot of really interesting things going on in terms of technology, in terms of various innovations that we all can take, that we can all support and learn about, study about. And today you have experts talking about these different things that can impact our future climate. So with that in mind, please scan. You should be able to scan this, and you can, that'll take you to our website. But I want to talk through this very briefly. If you look over here at session 1, so right here at 7:30, we're going up to the 7th floor, and students especially think about where you want to be in each of these sessions. So from 7:30 to 7:55, for session 1, we have climate arts and literature, and that's faculty from communications, English, and art. In room 724, we have avoiding the climate gloom and doom, social work, philosophy, recreation, and medicine. And in room 752, greener transportation, faculty from aviation and automotive. So again, students, please make notes, write on your hand, whatever you got to do. If you have a great memory, by all means, remember which rooms you want to go to at 7:30. So when we leave here, everybody will be going up to the 7th floor, and you need to pick one of those sessions. Then up at the top here on the right, session 2 is from 8 to 8:25. You can see that we have faculty from forestry, law, and history in room 722. I hope faculty are, so maybe if faculty want to leave, you have a map, you should probably wait a minute here. Let me just show you this very quickly. Here's how it works. We are where the star is, basically on the 1st floor. You can take elevators here and here, or you can go up the stairs to the 7th floor, and there is room 752, 722, and 724. To give you a better way of thinking about it, if you look out the windows here, you should see the clock tower, that's north. Does that help at all? Okay, so that's where we all need to go. But then let me go back so that you can all, oh, wait, one more thing. If any of you have questions, we don't have time for questions for me or Dr. Schoof right now, but here are email addresses. So make note of those. I'm Dr. Duram. Dr. Schoof's email address is there if you have any questions about any of the information you just saw here. Otherwise, please go ahead and look at these various sessions and keep track of where you want to be when. And I'm hoping now that all of the first session faculty have left. And that was what that mass exodus was. I don't know where students would be going right now. There's nothing up there yet. So anybody in session one, faculty for session one, have you all left? Oh, fantastic. Okay, great. So then students, just keep in mind if you want session one, which of those. In session two, I sort of read off some of those. And then the final session is 8:30 to 8:55. Session three is smart cities. And those are faculty from architecture. In room 724, consumerism and climate change with economics and sociology faculty. And then in room 752, water and multiple stressors, faculty from engineering, zoology, and geography. Okay, and again, you should be able to just scan that with your phone and it'll take you right to the website. Okay.
Thank you, Dr. Duram.
Thank you all for coming tonight.